Let's go ahead and review what we've talked about so far in Packet 9A. Two key questions. What is the series? What does the series converge? If so, where? And keep in mind, we are creating infinite series in an effort to better approximate values of well-known functions, and we're using parts of the infinite series to approximate those functions, and we call those parts of the infinite series partial sums. And we've talked about different ways to generate a power series. We talked firstly about using the template 1 over 1 minus x, which was generated by the sum of a geometric series. And then we differentiated every term of the power series, and we also talked about integrating every term of the power series. By the way, pause the video if you don't have your calculator handy, but you should have your calculator handy. But anyway, today is, in this video, we're going to talk about grinding it out, temporarily anyway, in the first part of this packet. Grinding it out, we're just basically going to take a function and we're going to try to create a polynomial approximation to that function. So this part of the video is a bit tedious, but it's important that you see what goes into generating the terms of a power series, just kind of like from scratch. Okay, so what I want you to do is take a look at the graph. Okay, let me see if I can zoom in a little bit. So if we zoom in on this graph and I ask you what function do you think that is, more than likely you would say y equals x. Okay, so if I hit the trace button though, you can see the coordinates of the point on the curve, and if I move to the right on the curve, you can see pretty quickly that the y and the x are not actually the same. They're almost the same. They look the same. That's why you thought maybe y equals x. But you can see that the y and the x are not exactly the same. So what we're going to do here is we're going to zoom out and see if we can get a better idea. Bringing the cursor back to 0, 0. Let's move it on down there, right around 0, 0. And if we zoom out and we keep zooming out, where do we get? What do we get? And let me pause the video and zoom out to a nice spot. Okay, so here we have what looks to be the sine of x, and indeed it is the sine of x. So let's go ahead and fill in a couple details here. So that looks like y equals x, but no. Do the values shown support your choice of the function? No, they are different. Okay, so x or y did not equal x. In that case, it was a small window. So is that a large enough window? No. So if we zoom out, we use a better viewing window to see that we do indeed have the y equals the sine of x. Okay, so now let's go ahead and just graph y equals sine of x and y equals x in the same window. Okay, and it looks like right in between here and here or so, like -0.5 to 0.5 or so, it looks like the two functions have about the same value. Okay, let me change papers here. So basically we can see that the functions are pretty close, that the difference between the two functions is close to 0 near the origin, but not so good when we get away from the origin. So let's go ahead and let's set up our y equals to be sine of x is equal to y1 is equal to sine of x, and then y2 is equal to x. And then let's do this. Let's define y3 to be our y1 minus our y2. Okay, so y3 is going to show us the difference between the two. And move your cursor to the left and hit enter. And we want to make a solid line, big thick solid line there. so that we can see clearly the difference. And that didn't look like it changed at all. Let's see. So there's our y equals x. And then that black curve there represents the difference between the sine of x and the y equals x. Okay, so let's go ahead and draw that. And back up a little bit. So if we draw that, we've got sine of x. We've got the y equals x. And then we have the difference. Okay, something like that. And at first I realized this might not make a whole lot of sense to you right now, but if it does, great. So if you take the blue curve, which is the sine of x, and you take the red plus the black, you're supposed to get the sine of x. In fact, that's what you would get. The red plus the black would be equal to the blue, and you can see that the black represents the difference between the blue and the red. So when the difference is 0, so try to pay attention to this here. When the difference is 0 between negative 0.5 and 0.5, that's where the linear function is the same as the trigonometric function. Okay? If the difference is either less than 0 or greater than 0, then we have an error involved in our approximating the trigonometric function by that linear function. So we have an error here. So let's see how we handle that error. First of all, the shape of the black curve representing our error, what type of function does that difference resemble? Well, it looks like an x cubed, like negative x cubed. Okay, enter your guess in y4, how well does it approximate the difference? Well, if we put that into y4, x cubed, negative x cubed, and we want to know, well, how well does it approximate the difference? So I just graphed my negative x cubed, but we can see the negative x cubed is almost, it's got the same shape, but we need to add in a constant, and so we can see if we look down the page a little bit, how well does it approximate the difference? Not well. Use a constant of multiplication to make the graph of your function approximate the difference function and write your answer. So we're going to use negative x cubed over 6. Now don't worry, like, where did that 6 come from? Don't worry about it. A lot of trial and error. We're going to save all that time and just go right to it. So negative x cubed over 6, let's change our y4 and see if our y4, negative x cubed divided by 6, if we graph that, how well does that negative x cubed over 6 resemble our error? And if we think, oh, well, okay, the negative x cubed over 6 resembles our error, then we think, well, maybe we have a better guess at the polynomial that we use to approximate the function y equals sine of x. So the whole idea is we're trying to come up with a polynomial to use to approximate the value of the sine of x. So that's a better approximation. So that's all we're going to go with, though. And let's see, we have sine of x now, so approximates the graph in the window. It better approximates the graph. Let me back up a little bit. Okay, so we now have sine of x minus x is equal to this. And if we solve the equation for sine of x, we get sine of x is approximately equal to x minus x to the 6th. Oh, that should be a 3. X to the 3rd over 6. Okay? And so now let's do that. Let's add one more term. So we're building a polynomial that we can use, we think would be a good fit for the sine of x. Okay? So again, our goal is to come up with a polynomial to approximate the sine of x. So x minus x cubed divided by 6, and we'll do that same thing. We'll go ahead and graph all three, but I want to adjust my window so that my x-res is 3 so that it graphs it faster. So there's our sine of x, there's our polynomial approximation now, and we can see the black curve again is the error. Well, what does that look like? Well, you're supposed to realize that that looks like some fifth degree polynomial. So let's go ahead and draw that though. We've got our sine of x. Actually, the window that I'm showing on my calculator, you're supposed to be using a window of, let's say, like -3 to 3. And it would look more like that. Okay, so, and then the y values should be more of the same thing, -3 to 3. Okay, so we've got the sine of x, our approximation, and then the error again. So the error, we look at that and we think, okay, actually let me go ahead and draw that graph. Draw the graph of the approximation. So the approximation is better, okay, but then again there's still that error, and the error comes in here like this. Hardly any error for a while there, so the interval of convergence gets wider and wider. Okay, I'm going to stop the video here and continue. Actually, let me go ahead and finish this page here. Mark the intervals. It looks like more like -1.5 to 1.5 as the interval of convergence. And write a sentence indicating where the functions appear similar, where they do not. Basically point to that. That's where they appear to be similar. We're not going to use the table feature. We're just going to eyeball it to get a better idea, so we don't have to get bogged down with using our table feature. Okay, next video. So 9b, page 3, we just finished approximating the sine of x using a third degree polynomial, and then we see that, then we see that there's an error, and we're going to add another term. So I'm not going to walk through the rest of this piece by piece, but as you can see, we could keep repeating that same process, and we can let y4 be equal to x to the fifth over 120. We can get a better approximation by adding one more term. We can start to see a pattern. We can start to see, well, wait a second here, 6 is the same as 3 factorial, 120 is the same as 5 factorial, and we can start to come up with a pattern for the terms that we're going to use to approximate the sine of x. So let's go ahead and look at this. Let's add one more term, and we get sine of x is about equal to x plus, it should be a minus x cubed over 3 factorial plus x to the fifth over 5 factorial. So that's our current approximation for the sine of x, and all we have to do is this. And we just add one more